Now our goal for today is to sort of finish off our Taylor series in the sense of we're going to do one last Taylor series. And so what are the ones that we've done? We've done geometric, we've done e to the x, cosine x, sine of x, and now we're going to do 1 plus x to the power alpha, where alpha is just some arbitrary number. Now I will say that depending upon alpha, this can be very, very easy. For example, 1 plus x to the 1. All right, well that's 1 plus x. 1 plus x squared. 1 plus 2x plus x squared. All right, but of course, what about 1 plus x to the pi? Not so clear now. Okay, so let's just proceed. Now, how do we proceed? Well, we know our generic formula. So our generic formula says that f of x is our summation. K equals 0 to infinity. We take the kth derivative, and we're doing it starting at 0, so it's going to be evaluated at 0 times x to k over k factorial. So the main thing we have to do is say what's the right pattern here. So let's start by looking at our derivatives. So the original function, which we could by the way put as f0. Here that means 0 means 0 derivatives have been taken so far. And we'll say, all right, well that's the function 1 plus x to the alpha power. Now, the first derivative, what will that look like? Well, alpha comes down, so we get alpha 1 plus x, and then we subtract 1, alpha minus 1. The next derivative, well, the alpha in front still stays put, alpha minus 1, and 1 plus x to the alpha minus 2. By the way, I should have pointed out, if you're doing the chain rule, which you should, the derivative of 1 plus x is 1. So there's another times 1 on the outside, but it's redundant, so that's why I didn't write it down. The third derivative, well, okay, that's alpha times alpha minus 1 times alpha minus 2 times 1 plus x to the alpha minus 3. All right, there seems to be a pattern here. f4 of x. Well, alpha, alpha minus 1, alpha minus 2, alpha minus 3, 1 plus x to the alpha minus 4. Now, what's happening? Well, what's happening is we're starting to get these sort of longer and longer increasing products into the front. Alpha, alpha minus 1, alpha minus 2, alpha minus 3. So if we were to go all the way down to the kth derivative, what would we have? Well, we'd have alpha times alpha minus 1 times something. Now, let's be careful and figure this out, because we want to make sure we get this one right. If we think about what's happening here, you'll see when we had the zeroth derivative, there were no terms in front. First derivative, there was 1. Second, 2. Third derivative, 3. And so forth. So that says, in the grand total, that there should be a total of k terms out here in the front. Okay, so we know there's k terms. So what's the last one going to be? Well, here, you got to be careful, because we're not starting at alpha minus 1. We're starting at alpha minus 0. So it's going to be alpha minus k minus 1. So you can check if it's consistent, right? Because if I take the fourth derivative, it's the last term is alpha minus 3, 1 less. Third derivative, alpha minus 2, 1 less. Alpha minus 1, 1 less. So forth and so on. And then there's going to be 1 plus x to the power alpha minus k, right? See, fourth derivative, alpha minus 4. Third derivative, alpha minus 3. And so forth and so on. Okay, so that's our kth derivative, and of course we were to keep it going. So, finally, what do? Well, what happens when we plug 0 into our kth derivative? fk of 0. Well, you're going to get that constant in front. So you get that alpha times alpha minus 1, all the way up through alpha minus k minus 1, times 1 plus 0, which is 1, to the power alpha minus k. But here's the cool thing about 1 to a power. 1 to a power, assuming of course that the power is not infinity, is just 1. And therefore, that is our kth derivative evaluated at 0. And we're going to make the convention that f0 of 0 is where I have 0 terms, but we're going to make that to be 1. So, in some sense, we're like, aha, we're done already. That's fantastic. So, we'll have, and we'll write this as alpha minus 1, dot, 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 alpha minus k minus 1, and then there's an x to k. Now, I also have a k factorial, and I'm going to do something with the k factorial. What I'm going to think of the k factorial as is I'm going to start with k, then in the next term, k minus 1, dot, 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 to the last term, which is k minus 1. So you notice that this would be 1. So, that is the correct answer, but it doesn't have the most elegant form. Now let's sort of check and see what's going on. So, upstairs we have a product, and it's a product of k terms, where we start at alpha and go down by 1 at each term, right? Now, downstairs, what do we have? Well, it's a product of k terms. And what do? We start at, not at alpha, but at k, and we go down by 1. So in other words, they're sort of mimicking the same thing. So the top and the bottom, they kind of are very similar. The only difference is, instead of k, it's alpha. So it's almost like the top wants to be a factorial. So it's not a factorial, because alpha, we said, look, alpha is some fixed number, and that means alpha could be a very strange number. So it could be not necessarily a whole number. And when you do factorial, factorials have to be whole numbers. So what we've done is we've come up with a new notation, and here's our notation. So when you see this, we're going to just call this alpha k. And the way you read this is, if you want to say it out loud, so if you're having a conversation with your family, you're sitting around the table, and it's like, what did you study today in calculus? Well, we did alpha choose k. And that's what this refers to. In mathematics, this comes from the notion of, well, suppose I wanted to choose something. You know, maybe I have 7 balls and I want to pick 3 of them. How many ways are there for me to do it? And the answer is 7 choose 3. So that's where that's coming from. All right. So our final answer is that this is the sum, k equals 0 to infinity, of, we call it alpha choose k, x to the k. And that is our answer. And remember, that is 1 plus x to the alpha. Now, there are some things that you might want to ask. When is this true? And so we'll just note this holds, and we'll skip the details for now. But it always holds, definitely, if absolute value of x is less than 1. For any alpha, this is always true. Now, for some alpha, it holds even better. So we should do a couple of checks to see if this is somewhat consistent with what we've done before. So let's see, what's a good, reasonable check? Well, let's start with something that we probably could do by hand. 1 plus x cubed. Now, according to this would be the sum, k equals 0 to infinity, of, here, alpha is 3, so we say 3 choose k, x to the k. Now what happens to 3 choose k? Well, 3 choose 0, by convention, that's going to be 1. That's the empty product, so that's corresponding to like this 1 up here. How about 3 choose 1? Well, what you do is on the top, you start with 3, and on the bottom, you start with 1, and there's going to be one term each. So 3 choose 1 is 3. How about 3 choose 2? Well, top you start with 3, bottom you start with 2. You want 2 terms. So 2 times 1, 3 times 2. Well, that turns out to be 3. How about 3 choose 3? Okay, top is 3, bottom is 3, and there's 3 terms on each. And so you end up with 1. How about 3 choose 4? Well, okay, so top is 3, bottom is 4, and you want 4 terms, right? Because there's a 4. 4, 3, 2, 1. Downstairs, upstairs, 3, 2, 1, 0. Oh, 0. 0 is really hard to recover from in multiplication. It's 0. And in fact, what's going to happen is that 3 choose k is going to be 0 for any k greater than or equal to 4. So even though it looks like it's an infinite sum, most of the terms are 0. So what we end up with is for k equals 0, you get 1 times x to 0, which is 1. K equals 1, 3 times x. K equals 2, 3 again. X squared, k equals 3. And then you get 1 x cubed. And then plus 0, plus 0, plus 0, so forth and so on. So that's what you end up with. Now, if you're familiar with binomial theorem, you're like, hey, these are like Pascal triangle, those numbers that show up there. And the reason that it feels that way is because this is like Pascal's triangle. These are the numbers that show up there. And so this actually is sort of a generalization of the binomial theorem to where you say, look, it works for any choice for alpha. It doesn't have to be a really nice number. It can be a really strange number. All right, so that's sort of one check. Now let's do another kind of a check. So I'm going to do a little bit I want this here for reference. So we've done a series that kind of feels like a binomial series. So remember, we've done geometric 1 over 1 minus x. So I can think of this as 1 minus x to the minus 1. Or I can think of this as 1 plus negative x to the minus 1 power. So why am I doing this? Well, now what do we have? Well, here's our alpha. So our alpha is negative 1. And remember, alpha can be a strange number. Alpha can be negative. Absolutely, no problem. But now, instead of just x, we're going to plug in minus x. So, according to our rule, what would we have? This should be the sum from 0 to infinity of minus 1 choose k times negative x to the k power. All right, so now let's see if we can figure out what this should be. And hopefully it's not so bad, and it should be what we've seen before. So again, I'll do one more step before we try to simplify too much. So minus 1 choose k, and then there's negative 1 to the k, and x to the k. So let's try something. So minus 1, 0. Well, by convention, that's 1. So how about minus 1, 1? Well, upstairs you start with a minus 1, downstairs you start with 1, and you get one term. Well, we already have one term, so that's minus 1. How about minus 1, 2? So upstairs, minus 1, downstairs, 2. Now, that's our starting. How many terms do you want? You want 2 terms. So there's a minus 2 times 1. Then upstairs, we subtract 1. So minus 1 minus 2. So what's happening? Well, you're going to get the 2's and the 1's cancel. So you end up with a minus 1 times a minus 1, which is plus 1. How about minus 1, 3? All right, so we start with minus 1 upstairs. We start with 3 downstairs. We want a total of 3 terms, 3, 2, 1. So upstairs, minus 1, minus 2, minus 3, right? Because we want total 3 terms, and at every term we subtract 1. Again, the numbers cancel. The only things that don't are the signs. Here you have 3 minus signs. So you end up with a minus 1. And in general, what's going to happen is that minus 1k, well, downstairs you're going to get k, and you're going to end up with a total of k terms. Upstairs, minus 1, minus 2, and you're going to keep going till you get up to k terms, so you get to minus k. You see, the numbers are going to all cancel out. What doesn't is the sign. So you got k negative 1's upstairs, so you get minus 1 to the k. And that pattern always continues. So you end up with some from 0 to infinity, minus 1 to the k from the binomial coefficient, minus 1 to the k, x to the k, but these combined together, they're always 1. And so, lo and behold, we get the sum from 0 to infinity, x to the k power. So our geometric series is really a special case of the binomial series. Now, this is not me saying, haha, now we can forget geometric series. No, you should always remember geometric series because they're so important. They play a really nice pivotal role. The reason I'm talking about this is to say there's a beautiful consistency. So what you feel should be true in a special case will always be true. So like this is a more general result that still holds for the special case we talked about earlier. All right, well, let's do another special case. And now that we're getting warmed up, okay. Find the Taylor series for f of x, which is the square root of 1 plus x, about x equals 0. All right, well, this should be a nice, pleasant exercise for us. So what do we have? Well, we can say that f of x, this 1 over square root of 1 plus x, we can write that as 1 plus x to the minus a half. All right, well, what is that? Well, now we apply what we just learned. That's the sum from 0 to infinity of alpha is minus a half, so minus 1/2, choose k, x to k. All right, and now we're done. Aha, well, that was really quick. And we still have all this beautiful real estate here to play with. Well, since we have space, let's see if we can't dig a little bit into this minus a half, choose k. All right, so we're going to spend some time focusing on this. Is there a nice way to write that? So what do we have? So we have minus 1/2, choose k. So what are we going to do? Well, downstairs is pretty simple. It's k minus 1, and we're going to keep going until we get to k terms. So that's what the downstairs is. Now in the upstairs, well, we're going to start with minus 1 over 2. And now what's the next term going to be? Well, if you subtract 1, you're going to end up with minus 3 over 2. And then how about the next term? Well, that'll be minus 5 over 2. And you're going to keep going until you get to the very end. Now, we got to make sure we get to the right term at the end. So, what would the right term be? Well, I want to end up here with a total of k terms on top. So, I claim that this is going to be a minus 2k minus 1 over 2. All right. Now, why? Well, how can we think about it? Well, what we can think about is that this last term here, let's just do a little side computation. This last term here, I can think of it as I started with minus a half, then I subtracted k minus 1. Because what we're going to do is we're going to subtract enough. And this first term is minus half minus 0. Remember, there's that strange little shift. For you computer scientists, you won't think that's so strange. But for people who don't do a lot of computer programming, that's kind of takes a while to get used to. So, common denominator would make this, let's see, 2. So, right, so we get minus 1. minus 2 times k minus 1 all over 2. So that's what that would become. And let's see. Well, that's the same as minus 1 minus 2k plus 2 all over 2. And so, which is minus 2k plus 1 over 2. And now, if you factor the minus out, that's minus 2k minus 1 over 2. Aha! Just like what was going. Okay, good, good. So it checks out. Woohoo! Nice, nice. Now, back to work. Back to work. So, let's clean this up. So what do we have? Well, upstairs, there's all these terms here are negative. And there's a total of k terms. So I'm going to pull out all those negatives. So minus 1 to the k. There's also all the terms here have 2's in the denominator. So I'm going to pull that out, 2 to the k. And then upstairs, what do I have? Well, I have the odd numbers. 1 times 3 times 5 up to 2k minus 1. And then downstairs, I have, well, all the numbers from k. K, 2 times 1. All right. So, there we go. That's our expression. Now, but again, what we'd like to do, see our dream. We have a dream. And our dream is to say, do you see the dot, dot, dot? We'd like to find a way to write it without dot, dot, dot. Because that means that we have a nice compact notation. So dot, 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 it's a way to say, and the pattern continues. Well, we'd like to just say like, and this is the pattern. This is what it is. So downstairs, of course, we still have a really nice way to write this. This is the k factorial. So that's no problem. Now, what do we have upstairs? Well, if we look at this upstairs, we say, you know, it feels factorial-ish, right? It's not factorial, but it feels like a factorial. Now, why does it feel like a factorial and why is it not a factorial? Well, it feels like a factorial because we're multiplying a bunch of numbers together that are going up. That's what factorials do. But why is it not a factorial? Well, the problem is in factorial, we do all the numbers, and this is sort of skipping some numbers. And now we have our great, well, let's fix it moment. Aha! Let's try to fix it. So, how do we fix it? So, we still have the other stuff, minus 1 to the k, a 2 to the k, and I'll write this as a k factorial. And how do we fix it? Well, that's easy to do. What we have is we have 1, 3, 5, and then we have over at the end 2k minus 1. And the way you fix it is you say, let's fill in the gaps. So what are the gaps? Well, the gaps are the evens. 2, 4, there's a 6 here, and let's go ahead and finish it at 2k. So now, waha, that looks exactly like a factorial, but I can't just arbitrarily add numbers in. If I ever do that, I have to do something which would cancel them out. So you'll see the 2's, the 4's, the 6's, and the 2k's all cancel out. And now we're happy on the top. We're like, woohoo! This is a factorial. But you're probably thinking, Steve, you just traded one bad problem for another bad problem. Because now the bottom, that's not a factorial either. That also has the gaps. And you're saying, and the way to fix it is to fill in the holes, right? Well, if we did that, we'd just get back to where we started. But there's something really different here. Notice that all these terms up here were odd. And all these terms are even. Now, what's true about even numbers? Well, what's true about even numbers is that they're all multiples of 2. So what we can do is, okay, so let's write what we have. Upstairs, we have now a 2k factorial. Downstairs, we have 2 to the k and a k factorial. So that's from the first part. We have k terms here, and we're going to pull a 2 out of each term. So there's another 2 to the k. And what's left? Well, from the first term, I'm left with 1. Next term, 2. 3 all the way up to k. So, see, there's that nice advantage of even versus odd, even as we can pull out powers of 2. And now we say, ha ha ha, oh, this is a k factorial. So, what do we end up with? Well, we have a minus 1 to the k, 2k factorial. Downstairs we have 2 to the k times 2 to the k, which makes 4 to the k. And then we have a k factorial times a k factorial, which is a k factorial squared. And that's a very nice compressed way to write that expression. So, returning back to our original problem, that's equal to the summation, k equals 0 to infinity. And now we have a nice form. Minus the half choose k is minus 1 to the k, 2k factorial, divide that by 4 to the k times k factorial squared. And then there's an x to the k power. Ta-da! Wow, that's beautiful, beautiful. And see, we didn't have to take derivatives. We just applied the previous theorem because this falls into our previous category. It was all just about a matter of how do you make it look nice? How do you simplify it? All right, so now we're going to do some applications with this, and let's see what we can do. All right, so first, find the Taylor series for f of x equals 1 over the square root of 4 minus x squared about x equals 0. Now, this should feel very familiar. So we're going to just, for reference, we're going to copy what we did on the previous slide. So I'm going to write this as 1 over the square root of 1 plus something equals the summation k equals 0 to infinity of minus 1 to the k, 2k factorial, divide that by 4 to the k, k factorial squared times something to the k. Now, you might have a small objection and say, wait a second, Steve. Here you had x, and you replaced x by a box. Why are you doing that? Well, the reason is we want to say, look, we can change our names. So we want to be flexible and say, what goes into our box? It can be anything we want. It doesn't have to be x. If it is x, then it's exactly what you have written down here. But it could be something other than x. And so it's good to be flexible. All right, so that's what we did on the previous slide. Now, what are we going to do here? Well, we want to take what we've done and say, can I make this look like that? Well, there is a lot of stuff going for it. There's the 1 upstairs. There's the square root downstairs. Both good things. We run into our first problem, which is the 4. We don't want there to be a 4 there. We want there to be a 1 there. So how in the world do we change that from a 4 to a 1? Well, we can do the following. We can say that 1 over the square root of 4 minus x squared. What we'll do is we'll do some factoring. And we'll write this as square root of 4 times 1 minus x squared over 4. And because 4 is a constant, I can think of this as the square root of 4, which is 1/2. And then there's a 1 over the square root of 1 minus x squared over 4, right? So what you've done is essentially the 4 here came out as a half in front. Now, the half in the front, this part, we're pretty happy with. Now, why are we happy with that part? Well, because it's a constant. Really, it's polynomial. And we like polynomials, because when we're talking about making series, we're really talking about making polynomials. Okay, now the last thing is, this should be a minus x squared over 4. But remember, I want to put a plus there. So I'm going to think of this as a plus a minus x squared over 4. Okay, so what have we done? Well, we took what we were looking for and we made it fit our mold. So that 1 over square root of 1 plus something. And now we say, aha, I see what our something should be. What goes into the box is that minus x squared over 4. That's what goes into our box. So what we get is we get that this is 1/2, because that 1/2 is always there. Then the summation, k equals 0 to infinity of minus 1 to the k, 2k factorial, divide that by 4 to the k times k factorial squared, just copying what's in front here, times the something, which is minus x squared over 4, to the k power. Now, well, what do we end up with? Well, okay, we could, if we wanted to, bring the half in. That's perfectly fine. So that's summation, k equals 0 to infinity, 1/2. Now, we have a minus 1 to the k. We're going to end up with, well, let's go ahead and write this all out. There's another minus 1 to the k here, so minus 1 to the k. And then an x squared to the k, that's x to the 2k. Downstairs, well, 4 to the k. I'm going to be a little bit partial. Now, 4 to the k, we really got that as 2 to the k times 2 to the k, and there's another 2 here. So I'm going to think of that as 2 to the 2k. Then there's a k factorial squared. Then there's another 4 to the k, which again I'll think of that as 2 to the 2k. So this is the 4 to the k coming from inside. Well, if we put it all together, we see nice things start to happen. The minus 1s to the k's will undo each other. So we can think of them as canceling. I mean, they don't necessarily cancel in the traditional sense, but they cancel by, if you combine them, it becomes 1 to the k, and life is good. So we get a 2k factorial upstairs. Downstairs you have 2 to the 2k, 2 to the 2k, and one more 2. So that's 2 to the 4k plus 1. You add the exponents, 2k plus 1. And then there's a k factorial squared, and then finally an x to the 2k power. And there you go. That's the answer. That's the Taylor series that we were looking for. Now, a fun one. And this is a little bit similar. Find the Taylor series for the function f of x, which is arcsine of x, about x equals 0. We've done arctangent, but what about arcsine? Yeah. That's, well, it's going to be different. It's going to be fun. So let's think about what we have here. Well, we want to build off things that we've done before. Arcsine we haven't done before. So we start asking ourselves, is there something we can do to arcsine to make it look like things that we've done before? And, well, there's not really much in the way of algebra, but there is a little bit in the way of calculus. So in particular, if you take the derivative of arcsine, okay, all you arcsine lovers out there, do you remember what it is? The derivative of arcsine of x is 1 over square root 1 minus x squared. Yeah, I agree. It's not as nice as tangent. Definitely. But, okay, all right. Now, why is that useful? Well, it's pretty close to our mold we just did. In fact, it's really close. All we need to do is say, hey, that's 1 over the square root 1 plus minus x squared. And now we're ready to fit our mold. So, the derivative, that's the summation from 0 to infinity of minus 1 to the k, 2k factorial, divide that by 4 to the k factorial squared, and then the thing that goes into our mold is minus x squared to the k power. All right, well, again, we can do what we did before, so that's the sum from 0 to infinity, minus 1 to the k, 2k factorial, downstairs 4 to the k, k factorial squared minus 1 to the k, x to the 2k. And here we see that again the minus 1 to the k's combine and they end up canceling each other out. Alright, nice. Now, is this the answer? No. And not just because we should rewrite it, but it's not our answer because remember, we were after the function arcsine. This is not the function arcsine. What is it? It's the derivative. See that f prime of x. So we've now found a Taylor series for the derivative, which means we've got to somehow get from the Taylor series for the derivative to the Taylor series for the function. Well, how do we make that leap? What's the right procedure? The answer is we integrate. So now we have f of x. Well, that'll be the integral of this series, sum k equals 0 to infinity of 2k factorial 4 to the k, k factorial squared, x to the 2k dx. And remember how integration works with series is that you push the integration all the way in. So this becomes the sum k equals 0 to infinity of 2k factorial divided by 4 to the k, k factorial squared, integral x to the 2k dx. So that's the way that integration works, is you push the integral into the sum. Now, whoops, I have an extra big parenthesis there. Okay, there we go. There we go. Okay, all right. Well, we're okay. We're okay. All right, now, what's the integral of x to 2k? Well, that's the sum k equals 0 to infinity. We still have our terms up here, 2k factorial. Downstairs, 4 to the k, k factorial squared. And it's x to the 2k plus 1 over 2k plus 1. Are we done? No, not quite. Plus c. Now the question is, how do you find c? Well, the way you find c is you now choose a really good choice for x. So for instance, plug in x equals 0. Okay, so if you plug in x equals 0, what do you get? Well, you're going to get 0 for the sum. If I plug x equals 0 into the function, arcsine of 0 is 0. And so you get 0 is equal to 0 plus c, and therefore c equals 0. And therefore, lo and behold, our answer, our final answer, is in fact this sum. 0 to infinity, 2k factorial over 4 to the k, k factorial squared, x to the power 2k plus 1, divide that by 2k plus 1. Aha! Just probably not what we were expecting. Yeah, that's not so obvious at all. It's not so obvious at all. But if you're patient and you think about how can I manipulate, how can I combine information together, use a power series for a binomial series, add, subtract, make things work out, and life will be good. Okay, you won't be expected to memorize this one, but it's nice to know that you can do it. It's nice to know it's possible. It's possible. Okay, well, let's do another problem. So, find the first three non-zero terms of the Taylor series for f of x, which is equal to the square root of 10 minus x centered at 1. Now, we've got to be careful here because you'll notice something's a little different. We're not centered at 0, we're centered at 1. Now what does that mean? Well, really, that means we want to have things look like our expression will have things that involve x minus 1. So we're going to be a little bit extra careful. In fact, we could say the right amount of careful. So let's start with part A. So our goal here is we have our our function, well, f of x is the square root of 10 minus x. I want to express things in terms of x minus 1. So, how can I do that? Well, square root of 10 minus x minus 1. Okay, I replace x by x minus 1. But now I got to be really extra careful here. So, what have I really done? See that minus x minus minus makes really a plus 1. So I'm going to subtract 1. Or I'm going to write this as the square root of 9 minus x minus 1. All right, good. We're making progress. Now, if we think about it, this is the same as 9 minus x minus 1 to the 1/2 power. This expression here makes us think binomial theorem. And so we say, hey, we did binomial theorem. That says that 1 plus x to the alpha is equal to the summation, k equals 0 to infinity, of alpha choose k, x to the k. Now, of course, the x is just a stand-in. We can use any symbol we want. So we're like, ooh, this is really close. It's something to the alpha power. And so what's our challenge? Well, the minus, we want to make that into a plus, and the 9, we want to make that into a 1. Then we'd feel really good. Well, we know how to make the 9 into a 1. We've done that before. That was similar to a couple examples ago where we said, let's factor stuff out. And we also know how to turn the minus into a plus. The two wrongs make a right kind of philosophy. So we'll do it a little bit slowly here. So we're going to factor out a 9, then 1 minus x, minus, there we go. If you put enough parentheses, it's got to be true eventually, right? And let's see, if I definitely have a lot of parentheses. I feel like I have way too many. 1 minus x minus 1, right? I think I need one more parenthesis there. Okay, now I feel like it must be true. There are so many parentheses, it couldn't possibly be wrong, right? Okay, so let's be careful here. 9 to the half comes out in front as a, oops, I forgot. See, I factored a 9 out of the first term. I've also got to factor 9 out of the second term. So there's an over 9 here. All right, good. Sorry about that. Well, that's why you always are suspicious. Double check your work. 3 times, not minus, that's a plus. 1 plus minus x minus 1 over 9, and that's to the 1/2 power. All right, now we're okay after I've made a series of mistakes, but all right, we are back to where we should be. So we've written square root of 10 minus x in this format. And the reason we wanted to get into this format is so we could apply this idea. So this is equal to, we have 3 summation k equals 0 to infinity of alpha is 1/2 choose k times minus x minus 1 over 9 to the kth power. Now, we could try to simplify this, but let's keep in mind what we're trying to actually do. What are we trying to do? We're trying to find the first 3 non-zero terms. So instead of trying to simplify it, let's just plug in our first 3 terms. So what does we get? Well, if we plug in k equals 0, so we always have a 3, so we can think of this 3 here as coming in. So we're going to get a 3, 1/2 choose 0, and then we're going to get times 1, because this is to the 0 power is 1. Plus 3, 1/2 choose 1, and then we get minus x minus 1 over 9 to the 1 power. And then plus 3, 1/2 choose 2, and then minus x minus 1 over 9 squared, and dot, dot, dot. The reason dot, dot, dot is I only need the first 3 terms which aren't 0. And these don't look like they're going to be 0. So let's see what we can do. Well, a half choose 0 is 1. A half choose 1. Well, that's a half upstairs over 1 downstairs. And then we're okay. Good. So this is a half. A half choose 2. That's a half. And then downstairs 2, but we need 2 terms. So 2 times 1, a half minus 1 is minus a half. All right. So what do we have? Let's go through, work it through carefully. We're going to get 3 from the first term, because we have 3 times 1 times 1. From the second term, we have a minus, because there's a minus to the 1, so that's going to be a minus. We have an x minus 1. 3 goes into 9, so there's going to be a 1/3 downstairs, and then there's another half, so that makes it a 6. So minus x minus 1 over 6. Okay, for the next term, is it plus or minus? Let's figure that out first. So if we look at this binomial coefficient, if we clean this up, what do we have? Well, we really have a half times minus a half, that's minus a 4th, times another divided by 2, so that ends up being a minus an 8. So that binomial coefficient is negative. The negative squared means that's going to be a positive coming from that part. So put it all together, that's a negative. We end up with an x minus 1 squared. How about the number? Well, what do we have? We have a 3. And then here we have a 9 squared, that's 81. So we really have 3 going into 81, which leaves us with 27. And then you have 27 times 8. Well, what's 27 times 8? Well, 20 times 8 is, what is it? Well, 20 times 8 is 160. 7 times 8 is 56. You know, I gotta tell you, 7 times 8 has, for a long time, that was like the one number I could never multiply together. I always screwed that up. I always made a mistake. But, you know, if you know it's the one thing you always make a mistake on, then you know, and you pay more attention to it in the future. And the more you know, ... Now, I don't care about the ... What I care about is what are the first 3 non-zero terms. And so the moral here is that this is a really decent approximation to the square root of 10 minus x near x equals 1. Okay, good. And I see we've run out of space on this page, so let's use a new page to do part B. So part B says, hey, let's use this to get an estimate for what this integral should be. So here's sort of like in the application that we haven't done yet for Taylor series. You see the square root of 10 minus x near x equals 1, and this integral involves x, which is relatively near to 1. 15/4 might not feel like it's near 1, but it's in the same ballpark. So what we can do here is we can say, hey, all right, so, sorry, I'm going to make some notes here. So we're going to say that we're now in part B. The integral from 1 to 15/4 square root of 10 minus x dx, well, I can approximate it by replacing this square root of 10 minus x by what we've just found. So what we've just found is that this is the function of 3 minus x minus 1 over 6 minus x minus 1 squared over 216. So, in other words, because we know what this function is, the function is being well approximated by the polynomial, hopefully, and therefore the integral should be well approximated by this expression. So, okay, well, why is that great? Well, in some sense, we say, look, this is our bread and butter. These are polynomials. So, this is approximately, well, we just integrate term by term. We can do the integral of 3. In fact, what I can do is I can say the integral of 3 is 3 times x minus 1. It's absolutely true. The integral of 1 is really x plus any constant. I'm just using my constant to be x minus 1. And the reason I'm doing that is I want that to match what I have here. Then the integral of x minus 1 over 6, well, it's x minus 1 squared. You add 1 to the exponent, divide over 12. Integral of x minus 1 squared, okay, that would be x minus 1 cubed. Divide by 3. 3 times 216, of course, 648. And then you evaluate from 1 to 15/4. Now the nice thing is, because 1 is your center, plug in 1, all your terms are going to be 0. So what we end up with is 3 times 15/4 minus 1 minus 15/4 minus 1 squared over 12 minus 15/4 minus 1 cubed over 648. Okay, and at this point, it's not a pleasant computation. I did check, because I was a little bit curious about what this turned out to be. And if you clean this up and you're really patient, more patient than what we want to be, you end up with the following number, which is approximately, all right, 7.5877. All right. Now, at this point, you're like, okay, all right. What's the punchline? Well, the punchline is part C. Now, what is part C? It says, what's the exact value? All right. Well, let's see if we can figure that one out. So, that would be the integral. Let's put it here, give ourselves space. Integral 1 to 15/4. Well, 10 minus x to the 1/2. This is actually an integral we can do. It's actually involves almost nothing. There's no tricky substitution. It's because the inside is essentially 10 minus x. This would be 10 minus x, add 1 to the exponent, 3/2, multiplied by the reciprocal, 2/3, and then you have to account for the inside. You have to account for that negative. So put a negative in front. So minus 2/3 times 10 minus x to the 3/2 power. That's the antiderivative. Okay, all right, that's not so bad. And then we need to evaluate that, 1 to 15/4. So that's minus 2/3. We're going to do 10, subtract 15/4 to the 3/2, and then minus 2/3, 10 minus 1 to the 3/2. Now 10 minus 1 is 9. 9 to the 3/2. If you work this out, that's, well, square root of 9 is 3. 3 cubed is 27. And now if you multiply that, minus makes this a plus. 27 over 2/3 should make this 18, I believe, because you can take 3 goes into 27. That leaves you with 9. 9 times 2 is 18. Now how about here? Well, 10 minus 15/4, that's not just any number. So let's work on the inside. Really, that's 40/4 minus 15/4. That's 25/4 to the 3/2. And there's a negative 2/3. Now, let's start with the square roots. I can take the square root of the top and the square root of the bottom. So that would be square root of 25 is 5. Square root of 4 is 2. Then I'm going to cube that. And now I can take the actual cubes here. So let's see, that's minus 2 times 125. 5 times 5 times 5 over 3 times 8. Well, all right. First off, I can do that computation. So what do we end up with? We end up with minus 125 over 12 plus 18. Well, let's make a common denominator. So we'll replace 18 by, well, what is 18 times 12? Yeah, it's a big number. 216 twelfths. Right? Yeah, that's right. Okay, 216 subtract 125. If you do that, what do you end up with? You end up with 91 over 12. All right, so that's the exact value. Now you'll notice the exact value doesn't match the approximation. That almost never happens. You almost never have that the approximation and the exact value are the same. But let's look at what this turns out to be. If you plug into your calculator, and I did that earlier before I started today, you end up with 7.5833. So, what's the moral? The moral is that the approximation here versus, the approximation there versus the exact value, these are close. And now this gives us sort of our great, well, that makes sense. That makes sense because what's happening is we replace our function by a polynomial function that mimics what's happening. And it's a good approximator. And since it's a good approximator, our answer, if we replace our function with the reasonably good approximation, should be very close to what the actual answer is. Now at this point you're probably thinking, it seems though like the actual exact value was easier to find and would involve a lot less work. And that's true in this case. However, there could be cases where we couldn't find the exact value. One of the lessons that we hopefully learn from the first part of the course is that integration is tough. Very, very hard to do. And since integration is tough, what we should do is find ways to get approximation. Now, one thing we did was we did numerical approximation where we chop things up into little tiny rectangles. But that's incredibly inefficient and requires lots and lots of work. And our goal is, let's not do lots and lots of work. And so instead we should opt for something which gives us a reasonably close answer without having us to do too much work. And so that's sort of going to be our philosophy. We're going to do more examples of this where we use Taylor series to approximate functions and use that to find answers to problems that involve integration. All right, now that's it for the theory for today. But you know, we can't leave Taylor series without having just a little bit of fun. So, here we go. Suppose you have a number, we're going to call it I. And I is a number where I squared equals -1. Now you're probably thinking, ooh, that means that I is the square root of -1. And that's not quite true. That's a great story, but that's not the story for today. What we want to do is we want to use Taylor series to rewrite e to the ix, where there's some function f of x and some function g of x. All right. Now, before we get too far along in there, let's start with some facts about I. So, I to the 0 is 1. Whoops. There we go. I to the 1, we'll call it I squared is -1 because that says it right there. How about I cubed? What would that be? Well, I can think of it as I squared times I, which gets me to -I. I to the 4th, well, that's I squared times I squared, which is 1. Now, if you keep going, what you're going to start seeing is that there's this beautiful pattern here. So I to the 6th, we're to -1. I to the 7th, we're at -I. I to the 8th, we're at 1 again. And so forth and so on. In general, if I have I to 4k, so in other words, a multiple of 4 in the exponent, that's going to produce 1. If I have a multiple of 4 plus 1, well, that's going to be I. Multiple of 4 plus 2 will be a -1. And a multiple of 4 plus 3 will be a -I. Okay, so that's our pattern. Now, here we go. So, we have our generic formula, e to something is our summation, k equals 0 to infinity of the something to the k over k factorial. That's just our rule. We know it because we know that our exponential is one of our most important Taylor series. So we just want to make sure we have that down with a really solid understanding. All right, now let's begin. So, e to the ix. Well, that's our summation. K equals 0 to infinity of ix to the k over k factorial, which of course I can write as the summation k equals 0 to infinity of I to the k, x to the k over k factorial. Now, remember, what's our goal? Our goal is to break it up into two pieces, a function f of x and a function g of x with a single I. So we want to somehow not have I to some large powers, we just want to get down to i's. And here's why we said, oh, look, I has this sort of nice pattern here. And so when we sort of get into it, we can have this sort of alternating I minus I, 1 minus 1. So what we're going to get is, well, let's start with the first couple of terms and see if we can spot our pattern. So for 0, we're going to get 1. Then the next term, I to the 1, that's an I. So we're going to have plus I, and then there's going to be x to the 1 over 1 factorial. Now the next term, I squared. Well, that's a minus. And there's no I at all. So minus x squared over 2 factorial. The third term, I cubed. Okay, that's a minus I. Then we have x cubed over 3 factorial. Next term, I to the 4th. That's a plus 1, x to the 4th over 4 factorial. I to the 5th, well, that's back to an I again. So plus I, x to the 5th over 5 factorial. Next term, I to the 6th, that's a minus 1, x to the 6th over 6 factorial. X to the 7th, well, minus I. So minus I, x to the 7th over 7 factorial. X to the 8th, I to the 8th, back to plus 1. And we're going to see this pattern repeats. So what's happening is we still have that x to the k over k factorial, but our coefficients are going to be 1i minus 1 minus I, 1i minus 1 minus I, 1. And so the next term would be I, and then minus 1, and then minus I. And this is just going to keep going forever. Okay? Now, let us group. So there's going to be two groups. So the first group is the let's keep it real, man. So the ones without any i's. So those are these parts here. You'll notice that they are the even numbers, because if you look here, the even powers are the powers where we have no I. So what we get is we get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus x to the 10th over 10 factorial, and so forth and so on. And in fact, you'll notice we are going to alternate plus 1 minus 1 plus 1 minus 1. So we could compress this and say that this is the sum, 0 to infinity. We have even powers, even factorials, and then we alternate our sign. Okay, so that's the parts without an I. How about the parts with an I? Well, that's the other stuff, right? So first off, they all have an I in it, so let's just go ahead and pull out the I. So plus I, and then what do we have? We have x to the 1 over 1 factorial minus x to the 3 over 3 factorial plus x to the 5 over 5 factorial minus x to the 7, 7 factorial, plus x to the 9, 9 factorial, and so forth, and so on. Right? Yeah. Now, again, you see this plus, minus, plus, minus, plus, minus? Well, that's because, if you look, we're going to have that plus, minus going on, because we alternate between I and minus I. So we could, again, compress this sum. So this is the sum k equals 0 to infinity. And now we have the odd exponents, the odd factorials, and we still alternate sign. Okay. So there's an I out here in front. And then we have this part over here. And now this is our chance to say, have we seen anything like this before? And boy, I hope so. This first piece is the cosine. And this second piece is the sine. So what we end up with is we end up with cosine of x plus I sine of x. So you may have heard us mention at various points in time that there's this beautiful connection between the exponential function and sines and cosines, and that's the connection here. So we have all sorts of very strange facts. So here's one strange fact. If I take e to the pi times I, well, okay, so that's x equals 1. Cosine of pi is minus 1. Sine of pi is 0. So e to the pi times I is negative 1. What? Really? Yeah, really. It's amazing. It's totally cool. You can also derive some really fun facts using this identity here. So let's do that really quickly. Let's derive really fun facts. So let's start, and we'll just do a couple here. Let's try double angle. And this is not the only fun fact you can derive, but I just want to give you a quick example. So double angle. So you have, let's look at the following. We have cosine of 2x plus I sine of 2x. Now that, according to what we just did, that's e to the I times 2x. Because e to the I something is cosine something plus I sine something. Now here's the really fun trick. This is e to the ix squared, right? Because this is just multiplication. And I can turn power to a power as multiplication, which is cosine of x plus I sine of x squared, because that's what e to the ix is. And if you square that, well, that's a squared, 2ab, so 2 cosine x, I sine of x, and b squared, I squared sine squared. But I squared is minus 1. So that's cosine squared, and I'll combine it with the sine squared. And then there is an I here, and 2 cosine sine. So what happens is that the cosine squared x has to match with the cosine squared x minus sine squared x has to match with the cosine 2x. And then the other thing, of course, is that the sine of 2x, which is the part attached to the I, has to match with the part attached to the I. So in other words, if we use the language, the real parts have to match and the imaginary parts have to match. Let's do another interesting little tidbit here. And it's the following. If you do the fact here, so we have e to the ix, that's cosine x plus I sine of x. What's e to the minus ix? Well, replace x by minus x. Cosine, even function, so you're still cosine of x. Sine of x, well, sine is an odd function, so sine of negative x is minus sine x. So if we now add, then what we get is we get the following. Here, when we add on the right, the sine x's cancel, so we get 2 cosine of x is equal to e to the ix plus e to the minus ix, or we could say cosine of x is e to the ix plus e to the minus ix over 2. If we were to subtract the cosines cancel, here these combine, 2I sine of x equals e to the ix minus e to the minus ix, or sine of x is equal to, and you end up with e to the ix minus e to the minus ix over 2I. Now, if you dig really far back and you say, hey, I remember something from a long time ago, which was there's something called cosh and sinh, hyperbolic cosine, hyperbolic sine. So cosh is e to the x plus e to the minus x over 2, and sinh is e to the x minus e to the minus x over 2. And now, when you first see these functions and you say, that doesn't look like anything to do with cosine. Why would they call it cosh, hyperbolic cosine? But now when you say, oh, that's why. Because really, this cosine and this cosh, the big difference here is you replace, if you take this x and replace it by ix, you get that function. So that's why we say that the cosine and hyperbolic cosine are secretly the same function. It's just one of them is using imaginary compared to the other one using reals and vice versa. Now, we're going to almost stop here. I can't leave without making one last comment. Since we are doing Taylor series, if you were to do the Taylor series for cosh, it actually turns out to be really beautiful. So that's the sum k equals 0 to infinity of x to the 2k divided by 2k factorial. It looks a lot like the Taylor series for cosine, except for one thing. It's missing that minus 1 to the k. And the hyperbolic series for sinh, hyperbolic sine, well, similar idea. 0 to infinity, x to the power 2k plus 1 divided by 2k plus 1 factorial. And again, it's almost the same as the hyperbolic series for sine. It's just missing that minus 1 to the k. And so there's a lot of really cool facts that you can start exploring. So once you have this one basic identity, the fact that e to the ix is equal to cosine x plus I sine x, then there's just a lot of fun things you can play with. All right, well, that's it for today. And next time will be our last practice material, right? We've learned everything now. And so what's the goal? Next time we get into applications and see how we can use our Taylor series. And that's it for today. All right. See you then. Bye.